Okay, time to go over first Monday's homework question, which is pretty lengthy here, but let's see what we can do with it. And then we're going to move on to some new stuff. So, let's read this question. We have a positively charged object, henceforth referred to as object A, that has a charge of plus 10. Okay, so let's see what we have. So we have object A, and its charge is plus 10 microcoulombs. And then we have a negatively charged object, which is object B, which is a charge of minus 2. Okay, so QB equals minus 2 microcoulombs. Let's see, they are 1 meter apart from each other, with object A on the left and object B on the right. Okay, so this is the total distance between them, is 1 meter. So, first question. A third object with a charge of plus 1. Okay, so I'm just going to say this is object C. So QC has a charge of plus 1 microcoulombs. And it's half a meter to the right of object B. Okay, so we're going to revise this now. So this is the distance between A and B. So A to B is 1 meter. Now object C is 1 meter to the right of object B. So then this distance, which is B to C, is half a meter. Find the total electric field strength at object C's position. Okay, so the field strength at object C's position is the field created by objects A and B. Okay, because what would the field strength be at C's position created by C? Well, it would be infinite, right? If we're talking about specific answers, because what's the distance from object C to object C? 0, right? And you always divide by the distance. So, yeah, that doesn't really work. So what we need is the field from A. Oops. The distance here being from A to C squared. And we will need field B. B squared. Okay. So this is for part A. Well, you get the idea. Okay, this is all part A. So, let's plug in the numbers here. 9 times 10 to the 9 times the charge of A. So that's 10 microcoulombs. So 10 times 10 to the negative 6, which ends up just being 10 to the negative 5, divided by, now the distance from A to C squared. Now we have distance from A to B and distance from B to C. So the total distance from A to C is 1.5 squared. Yeah. So what does this end up being? Well, we have 9 times 10 to the 9 times 10 to the negative 5. So the numerator, I couldn't remember the name of the part on top of the fraction, is 9 times 10 to the 4, divided by 1.5 squared, which I'm going to be lazy and just do this, and that is 2.25. So therefore, 9 times 10 to the 4 is 90,000, divided by 2.25 gives you 40,000. Okay. Newtons per coulomb. And so what direction is this field? So let's see. The object A is on the left, and then object B is on the right, and the third object is placed half a meter to the right. Okay, so we have basically in order A, and then B, and then C. So we want the field from A all the way to C. It's a positive field, so it's going out of object A, which means it's going to be, this field is to the right. Okay, now the second one here, we have object B, which is, what's the charge of object B? Oh, it's -2. Now remember, for this I've said just ignore the negative. That just comes into play when you deal with the direction. Now the distance here is from B to C, right? B to C, and we have that as 0.5 already. So we have, let's see, that's going to be 18 times 10 to the 3 divided by 0.25. And I don't think this one's going to fit, but we'll see. So 18 times 0.3, that becomes 1.8 times 10 to the 4. So 1.8 times 10 to the 4 divided by 0.5, so that's 18,000 divided by 0.25, 72,000. Yeah, it's not going to fit. That's annoying. I'll just here. Just to keep it over there and look kind of consistent. Now this one, this is now from the negative charge. Okay, so we have A, which I dealt with, then we have B, and then C is over here. So B is pulling C in towards itself. So its field lines are towards the negative charge. So this one's going to be to the left. So what is our total electric field? We have this much to the right, this much to the left, which means our total electric field is going to be 32,000 newtons per coulomb to the left. Oops, don't need that extra spot. So this is your answer for A. Actually, I can mirror it this way. Okay, there. So it's consistent. Okay, consistency. All right, so there's your answer for A. Now B, what is the electric force on object C? Which direction would it move? Okay, so now, to get the force, you take the new charge and multiply it by the total field. So the new charge now is the charge for C. So 1 microcoulomb times the field that we just got of 32,000. This gives you, well, times that 0.032. That's your force. Now, and again, direction, what's the direction? Well, the rule for this is that a positive charge follows the field, while the negative charge does the opposite. So at this point, the field is pointing to the left, and we have charge C is a positive charge, so it is going to follow the field to the left. That's our answer for B. There you go. That's kind of working through this, see how you get an answer here and see how it comes together. Hopefully this is starting to make a little bit more sense and get used to this a bit more. Again, we will have some even more practice with this stuff. So even though I'm going to be moving into a new thing today, the stuff that we're doing today is definitely linked to this stuff. And we're going to still come back to electric fields going forward. So don't think, oh, we're done with electric fields. Now you have to know everything about them. That's not true at this point. Okay, so therefore, what are we starting? Down. So we're starting with voltage and electric potential energy. Here's your warm-up question. Now, electric field, how the point of this, in terms of what we've done with the electric field, is you can sort of do the electric field stuff to figure out at any point around any charges, you can find sort of an electric field. You can find what the strength of the field is, you can find what direction the field is in, you can find all that stuff. And then the point of that is that, okay, we have this field. If you put a charged object here, at that spot, we can then figure out the force on that object. Now, I'm telling you there's another thing called voltage. And now I'm saying, what do you think could voltage help us find, right? So electric field helps us get to the force. What do you think the voltage could get to? Now you might think, well, I don't know what the voltage is. You're right, but just think about this in terms of patterns and what information is on the screen right now, and use some deductive reasoning to figure this out. So, give you a bit to write in an answer, pause this, and then come back. Okay, so you may be able to see the pattern here. The whole idea is that electric field lets us figure out the force. And then the thing with the voltage is that the voltage lets us figure out the energy. Okay, that's the connection. So they behave very similarly, whereas you have some charged objects, they create a field around them, you can find that field stuff, and then from there, you can put another thing in, find the force on it. The voltage is the exact same kind of thing. The voltage is that you can have some charged objects, find the voltage around those charged objects, and if you put another charged object in that voltage, you can find its potential energy. Okay, it's the same sort of idea, it's just now to get with energy instead of force. So, let me kind of write this out in terms of new stuff. So, voltage is very similar to the electric field. Charged objects have voltages around them, and once you find what the voltage is, you can get the electric potential energy. Okay, it's the exact same kind of idea as the electric field and the electric force. However, there's two things that are different. The first is that, well, as you may imagine, since it is different, it's not the exact same formula. It is a little bit of a different formula. But the other thing, and this is something that is actually very nice. So, the main conceptual difference is that while the electric field is a vector, the voltage is a scalar. Okay, so all this stuff we've done in terms of direction involving the electric field, you don't need to worry about that involving the voltage. In other words, once you find the voltage, if you have to, for example, if you have to get to there's multiple charged objects, you have to find what the total electric field is, you have to worry about the direction of the field from every charge and all that kind of stuff. You don't have to do that with voltage. You just don't. So, let's first though, before we get into these further, let's actually get what the formula is. The formula for voltage is extremely similar to the electric field equation. It's just not R squared. Not R squared. So V is our voltage, and as you may imagine, with the name of voltage, the unit for voltage is volts, which is given as a V. A volt is sort of defined as joules per coulomb. So remember how the electric field was newtons per coulomb? The voltage is joules per coulomb. It's just that voltage has its own thing, whereas the field doesn't for some reason. We just call it newtons per coulomb and not something. So, yeah. K is again your Coulomb constant. Q is your charge creating the voltage in coulombs, and R is your distance from charge in meters. Okay, very, very similar to the electric field. Difference being, it's not R squared, and that it's a scalar. Okay, you may also notice that the electric field is therefore the voltage divided by R again. And so this is also why on the electric field lab, when it showed the units for the strength of the field, it had the units as volts per meter. That's why. So, yeah, we're not going to worry about that. Don't really worry about that connection because honestly, just mathematically and conceptually, it just kind of makes things more confusing. You can't switching between electric field and voltage. You can do it, but honestly, I think it's often like unnecessarily complicated. It just you could get things confused more than you think you would. So, let's do an example. Okay, let's say find the voltage 2 meters away from a 5 microcoulomb charge. Let's say plus 5 microcoulomb charge. Okay, well, voltage is kq over r, so 9 times 10 to the 9 times 5 times 10 to the negative 6 divided by 2. So, we get, well, I don't even need that at this point. 9 times 5 is 45, and then 10 to the 9 times 10 to the negative 6 gives you 10 to the 3, divided by 2, gives you 22,500, right? Yeah. There you go, there's your voltage. So, yeah, pretty straightforward in that sense. Now, you might be wondering, what if it's a negative charge? Because before I was saying for like the electric field stuff, oh, if it's positive, negative, don't worry about that. That comes out in terms of direction. But the voltage doesn't have direction. It's a scalar. So what if this was instead negative 5 microcoulomb charge? Well, this time you just put in the negative. So you'd end up with negative 45, and your answer would be negative 22,500 volts. That's it. That's the difference. So the electric field, I tell you to just sort of ignore the negative and figure that out when it comes with direction. For the voltage, keep the negative and just have it be negative. Have it be negative if if that's what it is. Now, the advantage of this especially comes into play when you have multiple charges. Okay, so let me copy this question here and sort of, but now instead of finding total field strength, let's find total voltage. Okay, so we want to find the total voltage, which means we have to find the voltage from A to C and we're going to have to find the voltage from B to C. Okay, so let's see what we get here. 9 times 10 to the 9 times charge. Still 10 microcoulombs, which I'm just going to skip straight to saying 10 to the negative 5. I think we get the point by now. Divided by the distance. Again, distance from A to C. So A to B was 1, B to C was 0.5, so it's going to be divided by 1.5. So this becomes just 9 times 10 to the 4 divided by 1.5, which is, well, 60,000. Now for this, we have, again, 9 times 10 to the 9 times, now QB is negative 2 times 10 to the negative 6, divided by, again, distance B to C, so it's going to be 0.5. So what do we have? We have negative 18, which I'll just do 1.8 times 10 to the 4, I believe that's how that works out, divided by 0.5. So, well, that's dividing by 0.5, which is multiplying by 2, so this becomes negative 36,000 volts. Right? All I did was just carrying the negative through and just having a negative answer. So then, what's my total voltage? Well, just easy. Just add them. And I mean actually add them like, how addition works with negatives. So, 60,000 plus negative 36,000. So what's your answer? 24,000 volts. That's it. You don't have to worry about direction at all. It's just, okay, it's 24,000 volts. Right there. There's your answer. Also, remember what you could is how... let me start over. Remember how there was a long kind of example I showed... was that yesterday? I think it was yesterday. The days are flowing together. Or I kind of showed you how to find where the electric field was 0, but it would end up being a really complicated quadratic. Let's actually do a similar question. Let's find, for these two charges, where is the voltage 0? The total voltage 0. And you might think, oh great, this is going to be another really complicated thing like the last one. It's not really. Remember, that's when, therefore, for these to equal 0, that means this number and this, one of these is going to be the negative version of this, right? So in other words, this equals negative of this. So negative B. Okay. So again, the k's both cancel out because they're both k's. So don't have to worry about this. Now, notice I'm saying negative of QB. QB is already negative. So I'm saying a negative of a negative. So just positive. So in other words, let me already put in numbers here. This is going to be 10 microcoulombs. And actually, I'm going to keep it like -6 so I can cancel that later. Divided by the distance. And that's going to be, again... Oh, we don't know the distance yet, right? So in this case, yeah. A. So we don't know this distance. And then it's going to be the negative of -2 times 10 to the -6. Oops. So in other words, just positive divided by RB. Now, the 10 to the -6's cancel, so we're just left with 10 divided by RA over 2 divided by RB. Now at this point, I had this up here before, up here where, well, the distance for A to B should add up to 1. So, wait, yeah, okay, yeah. So, so RA plus RB should equal 1. So what do we get? Well, you can just, smooth this around and say that, let's say RB equals 1 minus RA. So we have 10 over RA equals 2 over 1 minus RA. You can then cross multiply. So this becomes 10 times 1 minus RA equals 2 times RA. So in other words, 10 minus 10 RA equals 2 RA. I can multiply, if I add 10 RA to both sides, I get 10 equals 12 RA. So in other words, RA is just, well, 5/6 or 0.833 meters. And therefore RB is 1 minus RA, so it's going to be 1/6 of a meter. There you go. So again, it's not like super easy and great, but it's a lot better than the electric field one. You don't have to mess with the quadratic formula stuff. It's a much more simple thing here. So the fact that voltage is a scalar actually helps quite a lot in making this easier to work with than the electric field. Also notice from this that we have a situation, again, this is a positive and a negative charge, and how I told you how, let me actually open up the lab. I want to show you a thing with the lab. Lab, okay. Is that if I had a positive charge, let me put these in, okay. And a negative charge, I told you there was no way that the field was going to be 0 in between these, right? But, let's see, it was 10 and then -2, so let me just kind of put this up by being 5 and -1. The proportion's the same. But if I turn on voltage, you'll see there is a region where the voltage is 0. And I think you can kind of show, yeah. If I see, so there is a voltage between them, right? See, voltage is 0 about there. And I don't know, is that about 1/6 of the way over? How many spaces is that? It's like 1, 2, and a little bit more than 2. How many spaces are there total between this? That's 3, 4, 5, 10. So like, I don't know, what's like 2.5 divided by 15? Is that 1/6? That should be 6th, right? Yeah. So yeah, that lines up perfectly. So yeah, so you can have the voltage be 0 between though a positive and a negative charge, even though the field is never 0 between a positive and negative charge. That's something to keep in mind. So, and also notice, so the voltage does kind of relate to the field, because notice how like in here, where see the blue is showing you, oh, that's where the voltage is negative. It's I'm clear that the field is also pointing in towards there. And once I sort of transition from the blue to the red, you see how it sort of becomes, the field swaps direction. But even still, you can see here, for example, the field is 0 about here. About right there. Whereas over here, I can't actually get to another 0 point on the other side. About here. So it's not the same, right? It's close, but it's not the same. So that's something that you can kind of see from this, that mathematically it is similar, but they're not the same thing. And so you can see how that works there. And of course, by changing this, I can, change things around, and you'll see the blue kind of start to come in and be a bit stronger. That. And then is that the last one? So anyway, so yeah, so that's the kind of thing with voltage, how that works there. So just like how you can get electric force by multiplying the electric field strength by a new charge, you can get the electric potential energy by multiplying the voltage by a new charge. Okay, so again, going back to this problem here is, oh, we found this total voltage, and then, oh, look, we're putting this new charge here in that spot. So what is our voltage then? So how this works is your potential energy, and I'll say electric. It's just the new charge times the voltage. So going back to the example up here, I had my voltage was 24,000, and my new charge, which was QC, was +1 microcoulomb. So what's my potential energy? Well, again, it's just Q times V, so 1 microcoulomb, so 10 to the minus 6, times 24,000, which is going to be, what? 0.024. Okay, yeah. There's my energy. Just like that. So it's pretty straightforward, right? It's the same kind of process with the field and the force, it's just now with slightly different numbers. Now, the one difference here is that sort of the question of, okay, what about, how do the positive and negatives work here? Great, for example, if this was a negative answer, well, that means I would get like what? Like a, like a negative energy? How is that supposed to work, right? How does that make any sense? And that, you're right, that doesn't make any sense to have negative energy. So really, the whole positive and negative thing with the voltage, that's mostly in sort of determining like how voltages add together, right? So again, if I have the whole thing about a positive and a negative voltage, how is this going to sort of affect, right? How is this sort of affecting each other in that sense there? Now, and finding what the total voltage is. Now, once you have a total voltage, then you can kind of just, to get the energy, the positive and negative doesn't really matter. So in other words, no matter what I get for the voltage, I should get a positive or a negative number. That's fine. But whatever I get for the energy, whether it's positive or negative, you should just kind of say it's positive, right? Which, again, doesn't really make any sense, but that's because negative energy doesn't make any sense. So, because, for example, if instead I had, oh, what if my charge was negative and instead the voltage was positive, right? Well, in that case, it would also seem to be a negative. But again, it doesn't have negative energy, right? It's just a matter of, okay, the negative and positive in this sense, similar to how the force, it sort of determined like which direction it would go. This is sort of saying, okay, it has an energy. Once you let it go, it's going to go somewhere because of its energy. Which direction is it going? But the energy itself is still a number, right? And the number is 0.024 joules in this example. It's not negative 0.024 joules. It doesn't make any sense. So just keep that in mind in terms of negatives. The last thing I want to say about this is that the voltage has another name. Oops, I'm bolded still. The voltage is also called the electric potential. I hate this term, okay? Because, again, we were just talking about electric potential energy, okay? So electric potential energy and electric potential are different things, which is stupid. And I have no idea why they're called that. But that's what this is sometimes called. So I think even calling it voltage, like some people are like, oh, voltage is not the technical term. The technical term is electrical potential. But electric potential is stupid. So I'm just going to call it voltage because that makes sense. You know what I'm talking about then. You're like, oh, the thing with volts. Okay, yeah, that's easy. Whether electric potential is what, electric potential energy? No, it's not the potential energy. It's something else. So it's just unnecessarily complicated and confusing, and I don't like it. So I'm only telling you this because if you see just electric potential and you see that mentioned anywhere, or in like college they ask you to find for that, it's voltage. Okay, potential is voltage. Potential energy is potential energy, but potential is voltage. Okay, it's dumb. I don't like it, but that's what it is. So, okay, so at the end of the day now, what do we have? We have four terms. We have the electric field, and then we take that field and multiply it by a new charge. I'll put the Q prime there just to denote that it's a different Q than the other one, and you get the force. But now we also have the voltage, and if we multiply that by a new charge, we get the potential energy. Okay, so we have these four terms, and you can see that they're all very similar to each other. So we have, anything let me just there. So you can see how they're very, very similar to each other, and how you kind of get from one to the other. So the main thing for this, the difference for this also conceptually, is that these are vectors and these are scalars. Right, remember energy is a scalar. So yeah, and again, you may be tempted to sort of like, since you can say, well, if I take this and divide it by r, then I'll get to this here. And so, oh, does that mean if I take the potential energy and divide it by r, I'll get to force? Again, I think that's just unnecessarily complicated in terms of like moving between the two. So if anything, I would usually just kind of start from the ground up. Just start with the electric field formula, figure out the total field, and then get to the force. And then if you need to then find the potential energy, don't try to go straight from force to potential energy. It's just unnecessarily complicated because it's like which distance am I using, and all this stuff I just think it's not worth it. It's better to just then, okay, let me just start at the voltage, find the total voltage, and then get to the potential energy. So the work of it, what you're doing in terms of field to force and voltage to potential energy is very, very, very similar. Okay, it's just the equations are different, and the voltage and potential energy are scalars. Those are sort of your main differences, and sort of how that works there. I think tomorrow I'm going to maybe do a little bit more practice, sort of like how I had the electric field practice on Monday. I'm going to do a little bit more practice with the voltage and potential energy. And then Thursday, I'm going to give you sort of a practice worksheet on all four of these. Okay, so the worksheet is going to be submitted similarly to how the lab was submitted, which I know is not the easiest thing in the world to deal with, so I'll see how I can get that to work. But that's sort of the plan with that. And then Friday, we'll see what I plan to do on Friday. I'm not 100% sure yet. Originally, my plan, because this was all based off of last year's stuff, and because of last year, like the weeks were a little bit off. So, this week right now, last year was the week right before spring break. And so remember the week before, right before spring break, that Friday was off, right? So I'm like, well, I have an extra Friday. What am I do with it? So I'll figure it out what I want to do. I might just kind of go on to the next topic, but we'll see. I'll see. I'll figure it out. So yeah. And either way, if you do get the worksheet assigned on Thursday, I won't be expecting you to be done by Friday because it's fairly lengthy worksheet. I might just spend Friday just going over the worksheet, to be honest, because it's fairly lengthy. So yeah. Or I'll just have you do it kind of over the weekend, but we'll figure it out. Yeah. So, anyway, wrap-up question for this is... Where is it? I put it all the way down here. There it is. So, now I'm going to have you kind of look at this a little bit different way. So now I'm saying for your wrap-up question, you have a 1.5 volt battery. Okay, that's the voltage of the battery, and it's 5 centimeters long. If all of the charge in the battery, because again, you need a charge to create that voltage, so I'm making it simpler here, where I'm saying, okay, imagine all of that charge is on one side of the battery, then what must that charge be? Okay, so in other words, here's the voltage, here's the distance across the battery where you have the charge on one end and the voltage on the other. What does that charge have to be for this voltage to be 1.5? Okay. In other words, I've set this up conceptually so that the math you have to do is the easiest kind of math you would have to do in this scenario. Okay, so go through this, see what you can get, and work through this, pause this, and then I'll go over it in a second. Okay, so again, we're using this based off of the voltage equation. Now, how I've written this conceptually is that you're just kind of plugging stuff in as easy as possible. So, in other words, your voltage is 1.5. Your K is, again, 9 times 10 to the 9. That's always what it is. You don't know what the charge is. Okay, so we don't know what that is. And R is just 5 centimeters. They keep 5 centimeters, right? So it's 0.05 meters. So you got to kind of multiply this through and see what you get. So, what do we get? Let's see, 0.05. That was 1.5. 0.075. Equal 9 times 10 to the 9 Q, and then just divide by that to solve for Q, which is going to be divided by 9 times 10 to the 9 is 9 billion. Do you get that fun number? Yeah. That's your answer. Or 8.33 picocoulombs. If you want to go that small. So, remember I said that 1 coulomb is a really ridiculous amount of charge? Yeah, you can kind of see how this is coming into play here. So I got these numbers, actually, by just looking up a AA battery. So AA batteries have a voltage of 1.5 volts, and they're about 5 centimeters long. So, what this means then is that to get a voltage for that battery, this is it in terms of the charge you need. It's not a lot of charge, right? So, now granted, that's a good amount of electrons, right? If you're dividing this by 1.6 and then divided by 10 to the negative 19, yeah, so that is 52 million electrons. That's actually still kind of surprisingly small, right? 52 million electrons in a battery that are free? That's really not that many. So, yeah, I might be surprised that it's actually not a lot that you need for this to work, but there you go. So you can see how this works in terms of kind of finding charge from voltage, sort of working the equation back the other way. Okay, so going off of that, you then have your homework. You have a couple homework questions here. First one, we have a 5 microcoulomb charge 1 meter away from a negative 2 microcoulomb charge. What is the total voltage 0.2 meters from this, 0.7 mad, blah, 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 and then what is the potential energy? So this is basically, this question is very, very similar to basically the whole thing I was doing involving the voltage from this, where you have two charges. What's the total voltage from those two charges, and then you put a third charge in there. What's the potential energy? That's that question. And then this here, second question. I now have a 9-volt battery. It's that long, and again, what is the charge needed? How many electrons are needed to get this voltage? So again, you'd be dividing by the charge of an electron to get that. And then what's the potential energy? I forgot to mention this part here. Okay, so going back to this here. So once you have a potential energy, remember that from this, let me get it down. Okay, that potential energy. Unbold it. Can be set equal to kinetic energy to solve for velocity. Okay, so yeah. Now, so for example, again, we found this potential energy here. I could then say, well, this is equal to kinetic energy, which equals, 1/2 mv squared. So therefore, what's my velocity of this charged object once it gets going? Now, I would need to know the mass to figure that out. But if you have we're talking about electrons down here for this question here. So whatever potential energy you get on an electron, you could then say, okay, well, how fast would it be moving? You could set that equal to the kinetic energy 1/2 mv squared using the mass of an electron and solve for v. Okay, so you can see that works here. And I'm just going to keep this on one line just to make things easier. So that's kind of how that works there. So that's a little bit trickier to see if you can get that to work. But these are your two homework questions. They're in the form. And there you go. That's what we got for now. So again, more practice is coming. See what you can do with this. And yeah, that's it for today.